Hey programmers, welcome back to day 7 of the Advent of Code. Day 7 is my favorite day of the Advent of Code so far because I actually got to use some graph theory knowledge, which I explored a lot when I was studying computer science. It's kind of seldom useful in the real world, at least when you're kind of going through the web development sense of things. That being said, we're not going to really stay focused in on two of the kind of formal, graph theory elements of this problem. I think instead we'll just kind of approach it from the kind of programmer's point of view in terms of how we use it to actually just solve the problem. So I'll try to keep this nice and accessible. So what does today's problem input look like? Well, it's going to be a text file that contains many lines. Here's an example of one of the lines. So it reads, light red bags contain one bright white bag and two muted yellow bags. In the long run, we're going to want to answer questions about a bunch of bags in terms of, what bags contain other bags and stuff like that. And the reason I kind of thought about this as a graph theory problem is because I have multiple entities, mainly the bags, and I need some relationships between them. In other words, I'll say something like, hey, the bags in this problem translate to nodes of some graph. In other words, if I just wanted to visualize and set up some framework I can use to really understand, this sentence, I have basically a node for every bag color. So for example, I can have a light red node, and just to keep things a little clean, I'll just abbreviate these node IDs. So I'll call this li-re, or my light red node. And I'll create similar nodes for each of the bag colors in this sentence. So I have a bright white node, as well as a muted yellow node. And then from here, how can I actually establish a relationship among these bags? I think the most intuitive thing to do is sort of rearrange the nodes here so we can actually figure out what bags are inside of other bags. In other words, if the light red bag contains the other bags, then it kind of has edges that go down to them, sort of like this. So take a moment to understand how I translated this sentence into this visual graph. So far, this graph tells me that light red bags contain bright white bags as well as muted yellow bags, but how can I also incorporate the quantity of them? Right? I need to kind of establish the information that there is one bright white bag. Well, what I can do is just put number labels on the edges of this graph. So for example, I have one bright white bag and two muted yellow bags. And notice that the label lies between the nodes, right? And so from here, we have a reasonable graph. Let's start to work in some other statements from our problem input. So let's say I added one more, and I said that muted yellow bags contain 2 shiny gold bags and 9 faded blue bags. And I can visualize this similarly by just looking at my muted yellow node right now and listing some children below it. So I need 2 shiny gold bags, as well as 9 faded blue bags. Cool. So of course, you can build a graph basically using all of the lines in your input file. I'll just kind of go about coming up with an example for this very, very small graph. So let's say for now our input file only had these 2 lines, and so this would be kind of the full picture that we can generate from those 2 lines. What you also want to keep in mind is technically the direction of these edges flows downward, right? In other words, I'm having a node point to the other bags that it contains, right? And so along with that, let's actually figure out what problem we want to solve here. So part 1 of the Advent of Code for day 7 asks us to answer this question. How many bags eventually contain a shiny gold bag? And so the answer here, I'll go ahead and tell us, is 2. So take a moment, look at this diagram, and figure out how this diagram tells us the answer of 2. By the way, in this problem, they're really asking for the number of different bag colors that can eventually contain a shiny gold bag. And the reasoning is, if I kind of look at this diagram right now, it's really kind of more or less a tree, right? If I go to my shiny gold node, if I wanted to figure out what bag colors can contain eventually this shiny gold bag, well, there's going to be the nodes that are kind of up this chain. So mainly my muted yellow as well as my light red bag. So that's why the answer is 2. What you'll probably notice is right now, at least for part 1 of this problem, we actually don't need the quantity. So I'm just going to ignore the number labels that are on the edges right now. That's not going to be too useful. That being said, let's figure out what's a reasonable way to kind of implement how we can actually identify how many different bag colors eventually contain shiny gold. Well, visually, as humans, it's pretty plain to see, but what's like a hard and fast algorithm we can use to actually implement it? Well, I want to count just these nodes, right, that I have checked in green. And I don't really need to count any of the other nodes. But more importantly, we have to think about how, this tree can scale. So if I only want to count the number of bag colors that can eventually contain a shiny gold, you can imagine that in these nodes that I have an X, meaning that they don't eventually contain a shiny gold, they could have many other nodes listed under them, right? So I'm going to kind of generalize them as some abstract subtrees. So imagine my bright white node had a massive subtree below it, as well as my faded blue node having a massive subtree below it. I think in the long run, I shouldn't have to search any of these, subtrees that just don't contain shiny gold, because that would be quite a bit of extra work. And so what I also have to realize is when it comes to the direction of these edges, things kind of flow downward. In other words, nodes point to the other nodes that they contain. I think this is a really key insight to make here. If you want to actually efficiently kind of solve this problem, what you could do is just invert the edges. So imagine I took all of my arrowheads and made them point in the opposite direction, sort of like this. So now it's the case that a node is pointing to the bag that contains it, right? And now I actually have a really nice algorithm to kind of run through. If I begin at my shiny gold bag or my shiny gold node, what I can do is just keep following the path up this chain. So shiny gold points to muted yellow points to light red, and that should actually give me, along the way, all of the different bag colors that eventually contain shiny gold. So an important thing to notice that the answer we should return is 2, whereas in like the highlighted path I have 3 nodes, right? So what we really want to count is possibly just the edges that we take in this path, right? There are 2 edges I need to take here. That's how I can figure out that the answer is 2. And the really nice part about this is I was actually able to figure out all of the different bag colors that eventually contain shiny gold without traversing through those unnecessary subtrees. So at this point, I think it's pretty clear that we're getting a pretty strong tree vibe from this problem. And I think you'd be right in saying that. So before we go any further, I just want to mention that the input file for today is fairly long. Here's just a quick excerpt from what the file looks like. We can interpret all of these lines in the same way we did in just our last example. Probably the most annoying part about this problem is going to be to actually parse out all of the data, right? We're literally given just all of this text to figure out what colors point to which other colors. So we'll kind of, basically ignore that part for now. It's more tedious than anything. Really not that interesting when compared to the actual algorithm that we need to figure out and answer the question. That being said, you're probably wondering, we're kind of sketching things in this pattern of nodes and edges. How do I actually represent that programmatically? Well, if I had this structure kind of in my head, I can write that in some code by using just some classic graph representations. In particular, I can use an adjacency list. In other words, I can use some sort of like object. I really just need some structure that maps a key to its values, right? So what I'll do is make every node or every label of a node the keys of this object. So if you look in the bottom right corner right now, notice that all of the things before the colons just are the labels of the nodes. And what I can do is just go ahead and add a other node label into one of these arrays that are inside the value to represent that some node points to another one. In other words, if you look at the edges I have highlighted right now, let's say I wanted to store information for this edge. Well, it's telling me that bright white points to light red, so I could just add that in the appropriate array. Likewise, muted yellow points to light red, so I add that information. Shiny gold points to muted yellow, add that in. And finally, faded blue points to muted yellow as well. So representing a graph within our program isn't too fancy. I think at this point we're ready to jump right in and solve this one. So here we have our massive text file. To make this one more bearable, I went ahead and pre-prepared this parse line function. What it does is take in a single one of these lines and gives me the correct kind of information about the bag colors at hand. In other words, let's say I kind of copied this line. I think this is a good line. Let me kind of show you how my parse line function works on it. So if I called, maybe down here, if I call just the parse line method, it should just take in one of those lines, so just a string like this. Notice that this is telling me that dark turquoise bags contain 4 dark bronze and 3 posh tan. What an interesting color. Let's just console.log what this gives me so far. So I'll give this a run and see how that is parsed. So I'll do node part 1. And so notice that it gives me an object. So it's going to have my destination node, so the dark turquoise bag, which is the one that contains the stuff. And then the sources, I'll consider the other bags that are listed here. So do bear in mind that I'm doing that kind of inversion technique that we spoke about. I mean, although my dark turquoise contains dark bronze, right now I'm saying that the destination is dark turquoise and the source is dark bronze, right? So it's kind of as if dark bronze more or less points to dark turquoise. So I'm just going to go ahead and kind of take this function for granted. It was pretty tedious to make because of kind of how unformatted the inputs are, right? We could have as many bags as we want listed on a single line. Then we have kind of awkward things like sometimes it says bags or it says one bag singular, which just makes the code super duper annoying and not really that kind of relevant for the true algorithm at hand. So here's what I'll do. Let me go ahead and just call readlines. So when I call readlines, this will just give me an array of every line in the file, just like we always do, right? So I'll just await this. I'll call that my lines. And now I'll just use my parse line on every line. So quick iterations, I'll say for let line of lines. And let me just go ahead and invoke my parse line function. So this will give me back each time an object with the destination as well as an array of the sources. What I want to do is start to build the graph with that information. Just like we spoke about, I can create a graph and represent it by just using some JavaScript object where nodes are going to be keys of this object, right? And then what it can transition to will be inside of an array value. In other words, when I call my parse line, let me go ahead and destructure the information I get from it. So I get the destination, I called it, as well as these sources. Bear in mind that sources is the array. Now that I have this information destructured, what I want to do is point all of my source nodes to the same destination. Right? So I'm going to need some other iterations here. Let me just start by making sure that I at least properly initialize the destination in the graph. In other words, the first time I see a node, I should really check, hey, if we'll say destination is in the graph. So is that a key of my graph? So I'm checking if the destination is not already in the graph. And if it's not there, it would be good if I actually just add it there, right? So I'm going to initialize its value just to be the empty array. And what I really want to do is just iterate through every source node. So I'll say for let source of sources. So I'm iterating through all of the source nodes. Remember, they look something like this. And I want to kind of key into them in my object. But of course, I should probably check if they exist as well. So I'm going to steal this pattern. In other words, if it's the first time I'm seeing this source, then I can just go ahead and initialize that as well. Cool. What's really important to do for these like graph style problems is to make sure that every node is present as a key of your graph, even if it's going to point to an empty array. So that's why I'm choosing to write this kind of separately. But now that I have initialized the source within the graph, if it doesn't already exist, now I can do something like say, hey, the graph at the source points to the destination. Right, so what am I doing on this line? So I'm adding my destination node to the array that my source node has access to. So I think at this point we should have our completed graph. After I'm done adding the correct information from every line into my graph, let me just see what that graph looks like. It's probably going to be pretty huge. And I'll just be sure to run my solve method. So let's see what we get. It's going to be, yeah, a very, very massive object. Cool. You can see that apparently there's a lot of bags that just, aren't contained in any other bag, which I guess is totally fine. Now the point is, what I want to do is just implement that algorithm that traverses starting from my shiny gold. And it should just touch all of the bags that can contain a shiny gold. So let me create a function to do that. So I'll say const, I think we'll just call it, traverse, just traveling through this graph. And I'll give it a few pieces of information. I'm going to need to definitely know what the graph is, right? Those are kind of my rules for transitioning from one bag to the next. What I also want to do is track where I'm currently at. So I'll just refer to that as, we'll say, node. So what this is going to do is just travel as far as it can. And I think that should be all we need to pass into our traverse method. Kind of the punchline I'm looking for is over here, I'm going to be calling traverse, passing in the graph, as well as my shiny gold bag, which is somewhere in this output. Let me just double check that's actually there. So let me run this again, and then we'll actually, I don't know, grep for shiny gold bag. I think I left the word bag in all of these. Yeah, so definitely have some shiny gold bags. So I'll use that as my starting point. So add that into the mix, and then we'll just perform the traversal. I haven't really thought about what I want this to return quite yet, but here's the overall way we should call traverse. So I know I want this function to travel through the graph. The way I do that is to use the loop to visit all of the neighbors from my current node. So I'll say for let neighbor of the graph at the node. This should let me iterate through the array. In other words, let's say that my node was something like this dark blue bag. Then I'm iterating through this array, right? And I'm hitting my neighbor as each of these elements. And what I want to do is just travel through each of those elements. So I'll say traverse on the same graph, but now I'm going to be at my neighbor node. Cool. So I'm at least making my recursive call, right? Maybe at this point we should pause and think about if there's some base case here. I think I'll be good to go with this code as it is, because to me the base case is about having some node that points to an empty array, right? If that's the case, then this for loop has 0 iterations, so it just won't make this recursive call. Or really, the importance of a base case is it's just the absence of a recursive call. So as is, I think this code will be some safe recursion. That being said, now we want to think about what the actual return value of this function will be. I know that in the long run, I just want a count of things. So I'm going to think of things along the number data type, right? So I'll set up a nice number variable to act as my count. I'll say we'll say num bag colors. So I'm going to initialize that to 1, just to represent like the current node or current bag that I'm at. And then from there, I'm always going to assume that my traverse method returns the number of bag colors or unique bag colors in that separate part of my graph. So what I can do is say num bag colors and increase it by the return value of this recursive call. Notice that I'm going to be adding all of my recursive calls into this number of bag colors. And then from there, I think it's just a matter of us returning the num bag colors. Cool. So this code is looking pretty good. Let's go ahead and just see what it returns so far. So in the context of my actual expected output, we should be getting 101. I went ahead and figured out the solution beforehand. So I think if we run this code as is, we'll be a little off right now. So right now I get 110. And the reason is because we know that this structure is going to be like a graph. I could have like some duplicate nodes. So I could run into a node more than once. In the very classic kind of graph algorithm sense, we should track if we visited a node already. And so what I'll do is I'll track my visited, and I'll have that initialized to just a new set, because a set gives me really fast lookup. It's going to be constant time. And what I can do is say, all right, if I've already visited this node, in other words, if visited.has this node, then I actually don't need to explore it right now. I basically already counted it. So what I can do is just return, but I still need to return a valid number, right? So I'm going to return 0. If I return 0 for this node that has already been visited, that's okay, because I know that it's taken into account somewhere else in my traversal. But along with that, let's say that I'm visiting the node for the first time. That means that this if statement is false. So I reach this area of my code. And what I should do is actually add this node into my visited list. So I'll say visited.add my current node. And I want to make sure that all of my recursive calls have access to this visited information, sort of in a global sense, but I'll decide to just pass that along as an argument. And since I know JavaScript is kind of acting like a pass by reference language right now, this will allow all of my different traverse calls to access the same visited set in memory, right? Now that we added in the visited logic, let's go ahead and test this code. So I'll run part 1. Looks like we get an answer of 102, which is just off by 1 from our expected answer. And the reason is, right now, technically, we're also, because of this variable line 35, we're also counting the shiny gold bag itself, which we don't want to actually count, right? So our final answer is just going to be reduced by 1. In other words, I can just go ahead and return whatever the call to traverse gives me, starting at the shiny gold bag, but I just reduce it by 1 because I don't want to actually count that shiny gold bag itself, right? Recall what we said in the diagram. But if I run that now, we should get our final answer of 101. So pretty elegant algorithm. Definitely, one of those things where I had to stare at it for quite some time to kind of see the pattern. Important thing I want to take away is kind of don't focus too much on this parse line logic. Really, the core graph algorithm is just this function. With that, let's head back into the drawing board. We could talk about part 2. All right, let's work on part 2 now. So part 2 has us answer a different question. This time we want to answer how many bags are inside of a single shiny gold bag. An important thing to notice in this question is now we're asking for the bags that are inside of a shiny gold, whereas the last problem asks us to figure out what bags contain a shiny gold. So we kind of just want the opposite relation. In other words, when we generate the graph to answer a question like this, we should not invert the edges. Remember that in part 1, we actually chose to kind of invert the relation. Now we're not going to do that. In other words, what does that mean in kind of the abstract sense? Well, if I said that, hey, A contains 3B, then I have A point to B, and I can put 3 on the edge label, right? So this means that, hey, the A bag contains 3 B bags. Cool, so if you agree with that substructure, let's go ahead and scale this up. Imagine that we start with our shiny gold bag. So I start with shiny gold, and let's say that we were able to correctly create and generate the graph for this. It might look something like this. Don't forget that we also have the quantities on the edges for this graph, right? And those are actually going to be needed now to solve part 2. So just to make sure that we're understanding the graph in the same way, if you look at the left edge that comes out of the shiny gold, I can make a logical statement like a shiny gold bag contains exactly 1 dark olive bag. And so overall, if you wanted to actually just know the answer to this question of how many bags are inside of a shiny gold bag, I'll just go ahead and tell us that the answer here is going to be 32. So the final answer should be 32, but how can we actually derive that answer of 32 by looking at the visual graph? Well, I think the most important thing to do right now is to look at our graph and notice any very simple structures that we can kind of make a logical statement about out of the gate. In other words, if I look at the nodes at the very bottom of this graph, I can see that they don't contain any other bags. They sort of seem like a base case to me. So if I kind of highlight these nodes, let's say I look at these guys, I know that each of those don't contain any other bags, but they themselves are exactly 1 bag. So all of those count as 1, right? And now things get interesting. All I have to do is really just figure out some correct math to do all the way up this tree. In other words, just some quick calculations. So we'll trace through this. Let's say I stay focused on this left-hand edge over here. So it's telling me that there's exactly 1 faded blue bag, but it's telling me that, hey, my dark olive bag has 3 of those faded blue bags. Logically, in the context of like this structure, what I'm kind of doing is taking this 1 and I can multiply it by the 3, which kind of still gives me a 3, but that 3 can at least bubble up to the parent. And now if I look at the right-hand edge coming out of dark olive, I can do the same thing, right? I can take this 1, multiply it by the 4, and then bubble that up to the parent. And at this point, if I wanted to calculate how many bags a dark olive contains, it's just a matter of adding up these two numbers, right? 3 plus 4 is just 7. However, that's telling me how many bags dark olive contains. Dark olive itself is also 1 bag, so I need to also increase this quantity by 1. So let's do a quick sanity check. If we look above the node labeled DA-OL, or my dark olive bag, I have 8. That tells me that in this subtree, there are 8 bags, including this node itself, right? I have 7 nodes inside of my dark olive, or 7 bags inside of my dark olive, but then I have to do plus 1 for the dark olive bag itself. Let's carry over some similar logic along the right-hand side. So I know that on the right hand side, I can do the same thing. I multiply these ones by the label on their edges. And they just bubble up a 5 and 6 respectively to the parent. And I can just add them up. And when I take their sum, I'm saying that this node contains 11 bags. I also want to count this bag itself, so that's +1. So this subtree represents 12 bags. And now here's where things get really interesting. Let's analyze this left-hand edge over here. What I can do is carry over mostly the same logic. So I take this 8, multiply it by the 1, so I just still bubble up the 8 to the parent. And then along the other side, I take this 12 and I multiply it by the 2. That gives me 24. And I bubble that up to the parent. So from here, I can take the sum between these two. So 8 plus 24 just gives me 32. And this tells me that there are 32 bags within a shiny gold. Notice that at this final step, I don't, and I shouldn't, do the additional +1 because I don't want to consider the shiny gold itself. In this problem, they literally tell us to figure out the number of bags that are inside of shiny gold. It would be 33 if I also wanted to count the shiny gold bag itself. So at this point, I'm feeling really good about this algorithm. It feels very elegant, and I don't think it'll be that much work to actually implement. We can basically just implement this using some sort of like a depth-first traversal, or really just some recursive code that does these calculations. With that, let's head back into my editor. All right, so here we are inside of my part 2 file, and I haven't adjusted a parse line function. It's very similar to what we did in part 1, except I also included the amount as information inside, because you know that the quantity is important here. So let me show you how this one works. So if I call my parse line function, so I'll console.log parse line, and I'll go ahead and pass in, let's say just one of these lines. So let's say a string like this. Important thing to notice is this time around, we're not going to, invert the graph, so we don't need to do that in the long run. And I also want to include the actual number information. So let me show you what this gives back. So I'll run node on part 2. Cool. So notice that now it's the case that sources isn't just an array of the other bags, but rather it's an object where the other bags are the keys and the value is the actual quantity of that bag, right? So remember in this text it says shiny gray bags contain 3 dim, right? So my destination right now I guess is shiny gray, and sources would be dim pointing to 3, right? And likewise I have 4 muted turquoise. That's why in my object it says muted turquoise bag points to 4. Cool. And I wouldn't get too caught up with destination and sources here. I didn't really just change those variable names. The important thing is actually how we add those into our graph. So I think we're ready to just solve this one together. Again, a lot of tedious work is done in this parse line function. I had to write some additional logic to kind of handle the case where some node or some bag contained no other bags. There are a few lines like that in the input, right? For example, if I look for the word no, like faded salmon bags contain no other bags. Super annoying to handle. I couldn't really think about an elegant way to do that. So just an if statement for me, right? But in any case, over in our main function, this one's pretty straightforward because we don't need to invert the graph. So I'll create my graph object again, and I'll still iterate through every line. So I'll say let line of lines. Then as I iterate, I'll go ahead and parse that line just like we just did. And I can destructure out of that my destination as well as my sources. So notice that the data has this sort of shape. So sources is an object. Because I don't need to do any inversion here, I can actually just assign this data directly into the graph. So I can just say graph of my destination is going to equal the entire sources. Something like this. Cool. So the shape of the graph I get back, let's kind of see what that looks like. I'm going to console.log my entire graph, and we'll just run that code. So what does the entire graph look like for this input? Let's give it a shot. So I get this information. And so how can I interpret it? Well, for example, if I look at this little segment, it's telling me that clear lavender bags can contain 3 faded bags, as well as 3 clear bags, and also 3 dull bags. Cool. And then from here, we can just perform the algorithm that we spoke about on the whiteboard. In other words, I want to figure out all of the bags that are kind of under my shiny gold. So I'm still going to use a traverse function as a helper. I'm still going to call it. And And I'm going to pass in the same graph that we just created. And I'm going to have my starting point be the shiny gold bag, right? Nice. And I think in the long run, we're going to have an off by one kind of error again, so we can easily correct that. So we'll just keep that in mind. But the overall, logic of our traverse function would be what we described on the whiteboard, right? So let me just start by touching every node of the graph starting from this node point. So I'm going to use my for loop to iterate through, let's say, let neighbor in graph of node. So notice here that this time around I'm using the in operator to iterate through an object. So imagine that node is, let's say, my faded gold bag, right? When I key into my graph, I get back this object. So this highlighted object. If I use this syntax for let neighbor in this object, that means on the first iteration, neighbor is going to be faded salmon. Next iteration, neighbor is going to be light lavender. Cool. And then from there, if I wanted to also access the amount, I can just grab that separately. So let me say, we'll say const, maybe quantity, equals the graph of the node if I kind of transition to the neighbor. So the way I interpret this is, what is the quantity or the label on the edge that connects the node to the neighbor? A really nice graph object we're dealing with here. Nice. And so what we'll do is go ahead and call our function recursively on traverse, or rather on our neighbor. So I'll call traverse on the neighbor. So basically I'm now figuring out in this recursive call all of the bags, or the number of bags inside of that neighbor. But if I have quantity instances of neighbor, then I should multiply that result by the quantity. So again, what I'm doing here is I'm finding the number of bags in my neighbor's subtree, and I'm multiplying that number by the quantity that I have of the neighbor, right? Let's say I had 3, red bags. If each red bag contains 5 things, then I just should be doing 3 times 5, right? So this is kind of what this logic refers to. I just want to accumulate a total across all these branches, we'll say. So let me go ahead and create some count variable like last time. So I'll say, let's, count. And I still want to initialize this to 1, because again, I need to count the node I'm at right now, the bag I'm at right now. Then I'll do count plus equals this result. Notice that I'm going to do this for every edge that I can transition through. Then after my for loop, I should just be able to return my count. So really simply put, this traverse function implements the trace that we did on the visual graph drawing earlier. So one typo I'm noticing right now is when I call traverse, I should be passing in the graph as the first argument, so definitely don't want to forget that. And then the neighbor will become the next node in that stack frame. To test this code, we'll go ahead and just return what this call is, right? We're trying to figure out all of the bags, or the number of bags rather, that are inside of the shiny gold bag. And if this is working, what we should get is this quantity over here. Let's go ahead and check our work. So it looks like we're pretty close, and kind of like we anticipate, we just have that off by 1 scenario again, 37. And the reason is we're actually counting the shiny gold bag itself, because I initialize this count to 1, which is okay to do in most circumstances, except at like the tippy top of our tree. So I'll just go ahead and reduce this by 1, and then we should have our final solution for this problem. So again, similar to part 1, I think most of the work or hard work is done in creating this parse line function. And then afterwards, how we actually perform the graph algorithm is fairly short and really very canonical when it comes to graph algorithms. We're really just doing a depth first traversal through the graph, and also doing some arithmetic on the cost of those edges between the nodes that we travel through. All right, so I think that wraps up day 7. I'll catch you tomorrow for day 8.